Now we're going to get kind of heavy into our circuit diagrams here and see what happens when we hook up resistors in series and in parallel, meaning in combination with other resistors. Okay, so let's say we've got 3 resistors in series hooked up to a battery with some voltage. Now in series means that you've got kind of one after the other. You have 3 resistors hooked up to this battery. You'll say that one has resistance R1, R2, and R3. Okay. Now, around any circuit, the voltage drop, the potential difference between these two sides of the battery has to be the same as the potential difference going all the way around. Okay, that just kind of makes sense, right? Because you can't have 2 different potentials at this point right here. And so we can say that the potential difference across the battery is equal to the potential difference across each of these resistors altogether. Now, if we just consider continuity here, the amount of charge flowing through this resistor in a given time has to be the same as the amount of charge flowing through here and here. Just following that sort of continuity argument, you can't have more charge flowing in one spot in the circuit than in another spot that has the same another spot in the same series circuit. So we can say that each of these voltages is equal to that current times the resistance. So, and then we can factor out a current and see that this is the same as if we had a circuit where we just had one big resistor, which we call REQ for equivalent resistance, where that equivalent resistance is equal to the sum of the 3 resistances. So this is how you add resistors in series. So for resistors in series, the equivalent resistance of that circuit is just equal to the sum of all the resistances that are in series. All right. So I could give you a problem. We could say a 12-volt battery is hooked up to 3 resistors in series. The first one has a resistance of 12 ohms. The second one has a resistance of 25 ohms. And the current through the circuit is 35 milliamps. And I want to know what is the resistance of that third resistor. And we can figure this out just by applying that our equivalent resistance is the sum of the resistances. So we can say that that voltage of the battery is equal to the current times the sum of the 3 resistances. So if we rearrange that third value is equal to the voltage of the battery over the current minus the other 2 resistances, and then start punching those values in. 12 over 35 milliamps would be 0.035 minus 12 minus 25. So that third resistor, and this is a danger when you make numbers up. I don't know if this is going to be reasonable. It's a huge resistor. I apologize. 295.85, etc., or about 3.0 times 10 squared ohms. And, such resistors do exist, though they generally wouldn't be in a circuit with resistors of 12 and 25. But you can figure out what different resistances are. You can figure out that equivalent resistance. All right. Now, when resistors are in parallel, remember this was resistors in series. In parallel, what that looks like, again, let's say we have 3 resistors. This means there are branches in your circuit. And we have these 3 resistors. Now, if we consider the current traveling through this resistor, there's some current going on here, and then that current splits off into 3 branches. And just by kind of continuity, we can say that those 3 currents all add up to the total current. The current that goes through the battery it splits off into these 3 pieces, so that the current going through each of these 3 resistors adds up to that on a total current. Okay, and each of these currents is equal to the and the voltage drop across each of these resistors is identical. So we can say that each of these currents is equal to that voltage drop over the value of the resistor. We know V equals IR, and so the current is V over R. So we can say that that's equal to the sum of those 3 terms, that voltage drop over the current. And this total current would be equal to the voltage drop over what we call the equivalent resistance of this circuit. So this gets us our parallel combination. We can cancel out all of our E's, and for resistors in parallel, the equivalent resistance you can find via this inverse relationship, that the equivalent resistance is equal to 1 over R1 plus 1 over R2 plus 1 over R3. Okay, so 1 over the equivalent resistance is equal to the sum of 1 over each of the resistors. So that's how resistors combine in parallel. Okay. Now, that's all we're going to look at for today. Well, let's do an example of those. Let's say that our 3 resistors are 12 ohms, 25 ohms, and 15 ohms. And let's say our battery is 20 volts. And I want you to find the current, well, find all the currents. So I want to find I, I1, I2, etc. Okay. So, excuse me. First off, we can find our equivalent resistance. 1 over Req is 1 over 12 plus 1 over 25. Here, let me. Whoa, look at that. It's crazy. I can zoom in. Plus 1 over 15. So we can punch that in and find that our equivalent resistance, 1 over 12, look at this, plus 1 over 25 plus 1 over 15, 0.19, take 1 over that, and we get that our equivalent resistance is 5.26, etc. ohms. Now notice, combining resistors in parallel actually decreases the overall resistance, while combining them in series increases the overall resistance. So our equivalent resistance is that. Now we know that our total current is equal to the voltage over the total resistance. I should say the E, or epsilon, the EMF. And so that is just 20 volts over the 5.26, etc. And if I punch that in, I get that our current, oh, that's nice, comes out to 3.8 amps. All right. now that the voltage drop across each resistor has to be the same as the voltage drop, or as the voltage difference across the battery. So we can also say that our current 1 is equal to that voltage over R1, our current 2 is equal to the voltage over R2, and our current 3 is equal to the voltage over R3. And punch in each of those values. We've got 20 over 12 is 1.6 repeating. 20 over 25 is 0.8 amps, and 20 over 15 is 1.3 repeating amps. And if we add these all together, these two add up to 3. This adds up to, 3 plus 0.8 is 3.8. So those all add up and it works out well. Now it can get a lot more complicated when we have a combination of series and parallel circuits, and that's what we'll be doing next time. But for now, this is the conclusion of this little video segment, and this is what you will need to know for the upcoming class. So remember, I want you to go where am I going to do this? I want you to go on that, well, for now, just email me. I'm not sure where I'll have you post these in the future, but for now, just email me. I want you, each of you, your homework is to email me a question. All right, you need to email a question to Mr. P, which could be something you're confused about that I talked about, or maybe something, a further inquiry, maybe something that this brought up that you wanted to ask about, and I'm going to gear what I talk about next class based on what you say. Yeah, so I hope this is effective, and I'll see y'all next class.